Okay, I think we are ready to get started. Welcome everybody to the colloquium this week. This week's colloquium is drawn from the workshop Accretion Physics in the Era of JWST. And it's my great pleasure to welcome Vivian Yu. So Vivian is an observational astronomer at UC Irvine, and she got her PhD at Caltech. And you're an undergraduate at Caltech, and you got your PhD from the University of Hawaii at Manoa. And Vivian is an expert on the co-evolution of supermassive black holes and their galaxies. And she was a 2019 Havli Frontiers Fellow, and she was a 2020 Newcomb Cleveland Prize winner from the AAAS. And she's an experienced communicator to very broad audiences. So I think we're in store for a great talk today. For example, she was actually on PBS Nova recently and is about to be on TEDx. And she's going to tell us about background feedback from galaxy mergers. So please welcome Vivian.
Well, thank you for the lovely introduction, and thank you for having me here, giving me this opportunity to tell you about some of the work from our research group focusing on black hole feedback in galaxy mergers. A lot of the work that I'm going to tell you about today is done by these wonderful postdocs, especially Justin Cater and Marina Biankin. They're highlighted because they are here in the audience. So if you have any hard questions, please direct them to Justin and Marina. Okay, so I would like to start by emphasizing that while JWST is an excellent tool and an excellent observatory for probing the distant universe, because of the sensitivity, because it's how we can learn about the early times in the cosmos for the first time. It's also actually an excellent tool for investigating the detailed physics in the nearby universe, oftentimes hidden behind dust. So, for example, here is a galaxy merger. I'm showing, this is VV114, and this is a Hubble Space Telescope image. It was taken in the optical wavelengths. And here in the western component, because astronomers like to flip the compass rose, the western component, you can see that the stars are really bright. You can see all the star formation that's coming through in this optical image. But then the eastern component, on the other hand, looks very red and dusty, and in some cases dark, and you can't really see what's going on. If I were to show you what the JWST image looks like, all of a sudden it does actually look like a galaxy mergers, as you might expect, with all the light, infrared light coming through dust and reflected off the dust. And so I will now show you, hopefully, that what we can learn from JWST about these galaxy mergers. So I will start by what I'm not going to talk about today, which is a lot of the work that's done by my students. And so, but the astronomers in the audience, if you wanted to chat more about nuclear SEDs, if you want to chat more about spatially resolved gas kinematics, reverberation mapped AGN, or if you're looking for a wonderful PhD candidate, please talk to me afterwards. Okay, so let's start off with big picture that I think we can, maybe most of us in the room can agree upon, and this is hopefully not too unfamiliar to all of you. And so here is one of the biggest picture we can have of the cosmic history of our universe, starting with the Big Bang and going past dark ages, and then coming to the epoch of ionization. We start seeing some of the first stars, first galaxies, and then when the universe is still relatively small, and then they start expanding. Galaxies evolve all the way to present date. And so for me, I study nearby galaxies, so within the past billion years or so of the cosmic history, but it's quite, a marvelous phenomenon because of finite travel speed that we can look into, the distant universe, and we can actually be seeing back in time. And so if I were to put a telescope, I'm going to move this mouse if you don't mind. All right. Close enough. Okay. So if I were to put a telescope right here and kind of look down the barrel, and I would try to start counting up light from stars, for instance, I might get a broad view of what the cosmic history looks like in terms of amount of stars that have been formed throughout history. So this is a plot from a decade ago now that showcases the star formation rate density as a function of look-back time. Now, of course, this was a decade ago, so recent JWST observations have probably made things a little bit more interesting in the distant universe end. But for the most part, what we find in this case is that star formation peaks at around a time when the universe is about half or a little less than half of its current age, in a period that astronomers like to call cosmic noon. So if you were to decompose these galaxy populations where the stars are forming into different subpopulations, you would find that especially around this cosmic noon period, that these star formation density reside in galaxies that are very bright in the infrared. So we call them the luminous and ultraluminous infrared galaxies. And of course, the question that naturally arises is, why do we, what makes these galaxies so bright, and what makes them seem to govern the star formation history in our past? And what is really causing that infrared luminosity brightness? So one theory, I should say one framework that we've been working in the last few decades is sort of this a scenario of galaxy mergers. So if you have your normal blue spiral galaxies, sort of like our own Milky Way, they're blue because there are a lot of gas in there. They're always forming stars, and when they're forming stars, the young stars give off UV light, so that's really hot, appears blue, etc. And when they come into contact with another galaxy within some gravitational potential, then they start to interact with each other. So what they do is that they kind of go through this first passage, and then they do this little dance, and then they would go through a second passage, and then eventually they would collide and merge. During this process, that's when things get really chaotic. You have gas and dust that are losing angular momentum, and they're kind of funneled towards the center, triggering vigorous star formation, what we call starbursts, and that stars are again forming a lot of young stars, and that are actually getting reprocessed by dust. So that's why a lot of the light that's coming from these stars come into and make these galaxies look infrared bright. And then some of this gas also gets triggered into the center of the system, where we see a lot of dust, and also where the central supermassive black holes lie. So just to set the scale, when I say supermassive black holes, I mean black holes that are with masses like 1 million to 1 billion-ish solar masses, give or take. These are usually found in the center of these systems. How they merge, that's another interesting story. But at least in this scenario, we're talking about these mergers with the supermassive black holes getting a lot of gas accreted onto them. They eventually turn into this active phase, and then they appear really super bright and like what we call quasars. And then all of the it's powerful enough to drive winds, driving out all of gas. And then eventually, depending on whom you talk to, whether there's pristine gas coming in as well, maybe left with what we call red ellipticals, where they're no longer forming new stars, so they appear red because what exists is just passively evolving. Stellar populations just getting old, and then they appear red and gasless. So this is kind of the merger framework that we work with, and this applies to mostly galaxies galaxy pairs or in groups that have mass ratios about maybe 1:4 or smaller, 1:1 or so. So we put together this story from basically getting snapshots of these galaxy mergers, but we rely on our theorist friends to put this into a theoretical framework. So we know that this sort of process takes about a billion years, give or take. And what happens is that it's really during these merging phases, when these galaxies appear luminous in the infrared, that there's a lot of star formation activity going on. It's greatly enhanced those starburst episodes I just talked about, and also there are things happening with the black hole as well, and maybe something's happening with accretion that also happens to the obscuration of the nuclei. So this is what really interests me in understanding how galaxies evolved. So we have a picture of the observable galaxies kind of history, and we want to understand it by studying galaxies. But why do we care about black holes? So there's actually observational evidence where the mass of the black holes actually correlate relatively tightly with the properties of the galactic bulge in which they reside. And so this is one of such scaling relations. It seems this relationship seems to hold to be fairly tight over orders of magnitude. And so we see basically this tells us that, well, maybe galaxies seem to grow with their black holes. Larger galaxies have larger black holes, smaller galaxies have smaller black holes. And so this is maybe what gives us an idea that, okay, maybe there's something to do with the galaxies feeding into black hole. And this is actually quite a surprising phenomenon, I think, to a lot of us, which is that if you think about, the size of these different entities, we're talking about, something on the order of like a light day or like that type of size versus, tens of thousands of light years size, and yet they somehow know about each other. So is it, chicken or the egg? We really don't know, the origin of this sort of relationship. On the other hand, we also see on a much larger scale, if you look at cosmological simulations and you try to reproduce the luminosity function of galaxies, how bright these galaxies might look, and how many of the bright galaxies are as a function of the luminosity of the galaxy, see that what's been predicted actually over-predicts what we actually observe in the blue line in both the low luminosity end and the high luminosity end. And this, to explain these phenomena, we have been invoking supernovae feedback. So basically, from stellar evolution, stars explode, they drive off winds, and that might be enough to get rid of or to explain the discrepancy that we see in the low luminosity end. But at the high luminosity end, we seem to have to invoke AGN feedback. So the feedback that's coming from the black holes in order to say, okay, gas is getting removed, and then we're quenching star formation. Therefore, we don't see as many high luminosity galaxies as we might expect to see otherwise. So, this feeding and feedback loop is something that we would really like to understand in more detail. And of course, the universe is also not that simple, just not two arrows, but in fact, it is a lot of arrows. Otherwise, I think we astronomers might be out of a job soon. So this is a complicated system. I explained a little bit of how, gas forming stars, and then, that maybe supernovae that drive out gas, but then some of it also to forming the black holes that also drive out gas, and depending on how much energy and how much momentum you might be driving into that gas, some of it might get recycled back like a fountain, some of it might get ejected out and removed completely from the system. And so basically this is to reinforce the fact that galaxies are not static entity. They are these dynamic objects that we're trying to understand as an ecosystem. In fact, this is why one of the 3 priority areas that the astronomical community has come together to try to, and writing our decadal survey a few years ago, that we really want to understand how galactic ecosystem work in order to unveil the driver of galaxy growth. Okay, so my interest in this is really to understand, this is already messy. I want to understand how this messy system plays in galaxy mergers, which are also messy. And in other words, what is the role that galaxy mergers play in this process? Does it enhance it? Does it not? And because of how the dramatic changes that merging mechanism introduces to a galaxy's lifetime, what is the detail of how these sort of ecosystem plays out in mergers? So again, we looked at Theo's friends, and they sort of also have a framework where how this process actually works. Now I'm going to start the video. You're going to see the stellar simulation on the left and a simulation of a gas on the right. So this video beats 100 pictures, and so you can see that this is really what I was trying to tell you about encountering of two galaxies and emerging of two galaxies. Here you can see in the stellar light what we might expect to see, but more interesting to me is the panel on the right-hand side where you're seeing what gas, the merging process does to the gas during this process, and the different colors here respond to different temperatures. And so, so not all of the temperature, not all of the multiphase gas, as we call it, it's actually doing the same thing. And if we were to put this down into the temperature density phase space, you can see that a lot of the gas is recycling in what is this warm region. I would say that hot, warm, cool, dense, depending on whom you talk to, you may get different definitions of that. So make sure you specify this is like, few thousand Kelvin or vice versa. But in any case, what we see is that interactions do, in fact, enhance star formation. They seem to not alter the cool gas content so much, but they also, because of the simulations, we can track really the rate of change of that gas in the different phases throughout the process, and see whether or not some of the cold gas can still be used to fuel star formation, etc. And so coming from the observational side, this is really exciting. It means that there are hopefully the predictions that are being made and that we can hopefully use to constrain with our observations. So I am part of the Great Observatory Skylark Survey team, where we have amassed a number of multi-wavelength data sets for the nearby luminous infrared galaxies, most of which are galaxy mergers. So in our survey, there are about 200 nearby galaxy mergers, as you can see from this really nice gallery put together by with Hubble Space Telescope images. And what I really like about this the sample is that we do have really extreme mergers doing really crazy things, or relatively normal looking galaxies and everything in between. And so this sample allows us to build up the statistics that we need in order to understand those what happens to mergers at different phases of the process. So for goals, we are a multi-wavelength survey. We have a lot of observations from X-ray all the way to radio. And I'm happy to say that as of last year, we also have, a neutrino-related paper. Don't ask me anything about it because I'm not an expert. But I was happy to learn that ULIRCs, these ultraluminous infrared galaxies, are a good source of neutrinos. I am a infrared / optical astronomer, so I will particularly be telling you about some of the work we've been doing with Keck and JWST. Okay, so co-feedback, very complex. Try to narrow this down for this talk into a few different questions. How does gas get transported, power at different scales? How do these outflows couple to the multiphase interstellar medium, and also subsequently influence the host galaxy? And also, how does what role does galaxy interaction play in this feedback process? Hopefully, I have some answers for you towards the end of the talk. Okay, so first, I want to set the stage by showing you what we knew before JWST. Then I'll show you some results from the past 2 years of work, and then some of the most recent work that we've been doing. Okay. So this is one of my favorite ULIRCs. It is Macarian 273. Looks like a toothbrush with a long tail, and it has a really interesting nuclear system, which I'll show you in just a bit. But what I want to first introduce you to is integral field spectroscopic data. I've been told that I shouldn't never mention that phrase to anyone who's not an astronomer, observation astronomer, that I think this audience can handle it. If you're not used to seeing integral field spectroscopic data on a daily basis, then maybe this is a good primer. So usually you have spectroscopic data, so you have 1D data, you have imaging data, you have 2D data, and you have IFU data, so that is 3D data. And all it is just you have a spectrum at every pixel or an image at every wavelength, however you want to think about it. If I were to start this little movie and slide through this this image where I'm heading across an iron line at around 1.64 microns, you saw how the gas was moving. I'm going to play that again because I really like it. So as you go through the iron line, you can see how the gas is actually moving. That is in the center of Macquarie 273. And so just to kind of set that up, project that into a 2D plane, here is a map of that iron to flux that I was just telling you about. And then here is the velocity field. So you can interpret that as basically the motion of the iron gas. So things that are blue coming towards you, things that are red going away from you. So this is basically a classical signature of what you might expect from a Keplerian rotating disk. And so this galaxy at the distance that it is, and also with the resolution that we have, we're actually resolving within the closed sphere of influence, in this case, 28 parsecs per pixel. And so we were able to try to measure mass of the enclosed mass dynamically using simple Keplerian assumptions. And in this case, we actually landed a black hole mass of about 1 billion solar masses. And this actually matches really well with an estimate from Maser, and that's kind of usually the gold standard of how you might measure black hole masses. So this is great, and we've applied this method to a larger number of galaxies. If you want to hear more about that, you can ask me later. But what I was interested in, besides getting black hole masses, was also in the gas dynamics. So here is, again, similar plots as what I was showing you, but now this is in molecular hydrogen. And this is a molecular hydrogen transition at 2.12 microns. It's a row vibrational transition. So again, you can see that there's a lot of gas, molecular gas in this region. This kind of extend this way. And then you see that's very similar kinematics. This is actually a little bit lower resolution data, so it's not as clear as last time. But what I've added as the third panel is actually the velocity dispersion of the gas. So this is the turbulence of the gas. So what we're seeing is sort of this enhancement in a biconical shape, and that tells us there's likely a nuclear outflow to the center of this galaxy. So this was pretty cool because previously what we knew about Macquarie 273 is that there is a X-ray active black hole sitting in this spot, but otherwise we didn't see any X-ray observations coming from here. So people were like, what's going on in this region? But now we found a dynamical black hole mass that's sitting in a very small region, and we didn't see outflows being driven from it. So this ends up being like a Compton-thick AGN, a very dust-obscured black hole that is able to be driving molecular outflows that we can see a little bit further from the nucleus itself. So we determined some properties of this molecular outflows. I'm not going to read off the numbers here, but the point is that we now have numbers and start to quantitatively compare simulations that are at similar resolution, tens of parsecs or so. Oops. Button. Okay. So that's what we were able to do with one source, together with Ann Medling and also other folks in our collaboration. We have gotten a lot more Keck time to try to image more of these systems. In total, we probably targeted around 30 some merging systems, 50 nuclei, all with resolution about tens of parsecs, 30, 40 parsecs. And in the infrared, we have a number of really nice diagnostics. So I didn't label these lines, but a lot of these lines are molecular hydrogen, or like the rocket lines, and also the CO band has to probe the stellar kinematics. So with this data set, we've been able to study molecular outflows and dual AGN, nuclear disk, shocks, feedback, etc., and black hole masses. For the context of this talk, I'll focus on the star formation rate as one consequence of feedback. So what we've done here is that we calculated the dust corrected star formation rate. In other words, what was the intrinsic rate of star forming behind the dust, and we were able to look at it as a function of merger class. So as galaxies are getting closer and closer to each other, or better yet, the projected separation between the two nuclei, and we see that this seems to be enhanced as you get closer and closer together. And so this might be a sign of positive feedback, meaning that as these mergers go on, at least at these nuclear scales, we're seeing signs of positive feedback, which means stars are being formed rather than being removed. So we wondered if that has anything to do with the AGN itself. Is this part of black hole feedback? So we look at basically how excessive the molecular gas is, how much shocks there are in relation to the infrared, the properties of the AGN. So in this case, try to look at if there's excess hydrogen and in different ways where we measure how strong the AGN might be, but we don't really see correlation. And so we were kind of puzzled, and we're like, okay, maybe this is a case where these infrared galaxies just have such dusty nuclei, we're not really seeing through and calculating things properly. And so we selected a sample of our galaxies with the most promising signs of nuclear outflows in various degrees. So Macquarie 273 and then a few others. And we're saying, hey, maybe we should look at JWST. Maybe we can then look past the dust a little bit better to really understand what the geometry of the central engine, et cetera. And really, this kind of allows me to get back to the question of how supermassive black holes grow and merges. And I think this is something that I've learned a lot actually in this workshop, trying to tie what we see at these scales to the accretion physics and also, just the inner structure of the AGN itself. Okay, so that brings me to December 25th, 2021. It was a Christmas day, and as most of you know, this happens to be a very important day in my career, in my life, perhaps. And my baby was born. She came early, and I think some telescope got launched. I don't know. Yeah. So in the last few years, we've been busy with JWST data. It's a good problem to have. I'm not complaining. We were one of the teams that were awarded the early release science program. At first, we targeted 4 systems, and we targeted specifically the nuclei of these 4 systems. These were selected to have like a variety of silicon absorption features just to understand different mid-infrared properties that we can probe with JWST. And since then, we have also gotten a couple of cycle 1 programs and cycle 2 program to really enlarge our sample. These were then selected to target different science cases. Nonetheless, we have now accumulated probably about just over a couple dozen sources where we can do these studies in a more systematic level. A lot of the results I'm going to be presenting to you today comes from the early release science program in cycle 1, but we're going to have more results soon. Okay, so that brings me to the last 2 years of work. And I'm also going to just focus on one source rather than multiple sources. If we have time at the end, if you're interested, I can show you more other galaxies. Okay, so here is 7469. It is maybe familiar to some of the reverberation mapping or other local CFERT experts in the room, where it's actually part of a galaxy merger. It does host a CFERT 1-ish, 1.5-ish AGN in the center, which what it means is that it's mostly face on, just like the host galaxy. And so because it's mostly face on, you don't see kind of the dust that's covering it the way I showed in UA1 before, so that the contrast between this image taken by Hubble Space Telescope in the optical wavelengths is not that different from the JWST image taken in the near-infrared wavelength. But we get a lot more information with our JWST observations because we have IFU data. So this is kind of a unique system because you're going to see that this is a an AGN that's kind of surrounded by a star-forming ring. But what have we learned before JWST data? And that's this is the Spitzer spectrum. So for a lot of our galaxies, we actually do have Spitzer data. So Spitzer was the previous generation infrared telescope. Fantastic workhorse. I'm definitely not complaining about it. But we, of course, have made a lot of improvements. And so this was a spectrum from Spitzer IRS. It's a spectrograph that was used on Spitzer. Then here is a comparison spectrum from JWST MIRI instrument. So you can immediately see we have better sensitivity, but we also have better spectral resolution. So a lot of the lines that we had seen previously were actually blends of like real lines. These squiggles you see, they're all real. They're not, well, these are noise, but any of these things you see, those are all real lines that we're now detecting JWST. And what I was so excited about, Mary, is that it is the first time we put an integral field spectrograph in space. So what that means is that besides getting at what kind of information, what kind of elements are in these environments, what we also see is how elements is distributed and how it's moving. So this is, as I said, we have images at every channel of the spectrum. So this is what we see for these three particular gas species in NGC 7469. So we picked out iron 2 because, as you know, a lot of iron in space is actually being locked up by the interstellar medium in dust grains. And so if those are heated by shocks, then it releases iron in gas form. So we can actually see this lit up in these sort of mission lines. And of course, I picked a cooler molecular gas line to compare to some of the observations that we've seen in near infrared, and then also another ionized gas trace the star formation really well. So both of these two cases, you can see that there's a star-forming ring that's surrounding the central AGN, but that looks very different from the molecular gas morphology, which is tracing the CO gas a lot better. So if we were to now look at the kinematics, now this row is exactly the same as what I just presented to you in the previous slide, but here now we can see that there's dominated by rotation in the ring, and also in the dispersion map. What's really interesting is that we see some enhancement in kind of this direction. I'll come back to that point in a few slides. Okay. The mid-infrared also allows us access to some of the high ionization lines that we've seen. In this case, I kind of divvied up the central region of this data cube into different apertures, and then I'm here showing the full MIRI channel 1 spectra, but highlighted in this box is the magnesium 5 line. Now these by high ionization, I mean that, hydrogen ionization, 13.6 eV, these lines, you need at least about 97, 100 eV to excite. So if you see these lines, you know that there is some really high ionization there, likely coming from the active black holes. So in this particular case, we see this kind of broad and blue shifted morphology, and we've done the mapping of it, so we know that this is actually gas that's coming towards us, and that's why it's really blue shifted and broad. We looked at all the high ionization species as a whole. They all have the similar profile shape, which is in contrast to the low ionization species that we see. And also we've plotted kind of the line width as a function of this ionization potential. So what we're seeing in this case is a decelerating stratified AGN-driven outflow. Again, we've calculated some of the outflow rate, also estimated a black hole accretion rate based on some scaling relations. So in this particular case, we know that this is kind of the picture that we've put together, with the AGN in the center that's driving winds because it's face on. It's basically driving winds right at us. There is shocking some of the interstellar medium in the nearby region. Then there's also a rotating star-forming ring that's a little bit tilted our way. Now, Stinson and Marina looked at some of the more higher resolution near-infrared data. So again, this is now near spec that's spanning wavelength regime from 1 to 5. So some of this overlaps with the region that we can observe with Keck from the ground. But some of this is also a lot harder to access from the ground because of our atmosphere. And so and you can also see a number of plethora of these features, including some of the different features that we may not be as used to from the near-infrared, basic near-infrared data. So in this case, Marina looked at, for instance, the hydrogen recombination line, Paschen alpha. She mapped the velocity field. Again, this is very consistent with what we saw in the MIRI data, but then she actually modeled it with a Keplerian rotation, and we see that in the residuals, you can see that these are leftover kind of spiral structures, which we're interpreting as an inflow like gas kinematics. So if this is an inflow, then we estimated the inflow rate, which happens to be much larger than the black hole accretion rate that we determined from the MIRI data. And so this is going to lead to gas being built up in the central kiloparsec region. As a result, it's likely going to keep feeding the activity that's going on in the central parts into the supermassive black hole. And she also used a number of near-infrared diagnostics lines. So these are just line ratios with iron and Paschen beta and molecular hydrogen and bracket gamma. And so we saw that basically, if you were to use this diagnostic and see where, what are the regions that correspond to star formation, active black hole, accreting black hole, and also shocks, that this is pretty much the consistent picture that we saw in the lower resolution data, but now we can really see where the shocks are hitting the interstellar medium. This is actually coincides with where we found a very compact radio jet structure, so as a piece of evidence that how the ET and the ISM might be interacting. One cool thing about the mid-infrared lines, as I'm learning to myself, is that it features these emission features from polycyclic aromatic hydrocarbons. So these so-called PA features usually allows us to trace dust. And so previously with Spitzer, we only know that they exist, but again, we don't have the spatial distribution. Now for the first time, we can resolve things much finer spatial resolution. So this is again that star-forming ring. Now this is shown in PA, a 6.2 micron feature, and so you can see how the dust is distributed. When you have different pairs of these PA features, you can start to constrain the sizes of the grains. And so in this particular case, Thomas Lai from Caltech IPEC, he has looked at how the grains are distributed as a function of the radiation field. And what we're seeing is that in low and less hard radiation field, we see grain sizes that is kind of distributed all around, but then once you get to harder radiation field, you're only left with a large grain size, which what this means is that AGN or areas that are pretty close to where there's hard radiation, we're seeing a destruction of these the smaller dust grains. One more result on 7469. This is maybe not so much related necessarily to black hole feedback directly, but this work done by Thomas Bond, who's also a former graduate student of Gabby's. He joined our group and he was looking at some of the imaging data from MIRI, and he was able to find basically new young stellar clusters that we had previously not been able to detect with Hubble because of the dust obscuration. And so now the total percentage of these, and we were able to use like stellar colors and stellar models to constrain the age of these star clusters to be about like 3 to 5 million years, meaning that we are able to find a lot more stellar population in these galaxies, and that has implications of how you might think of, the initial mass function of stars and how they might be forming, and what might be potentially an effect of feedback from the AGN, from the black hole. Okay, so now latest insights. I'm gonna try to be less excited because otherwise I'm gonna be too excited about this results. Right, so here is the last case study I'm gonna really show. This is VV340. It is a, let's just see, it's an early stage merger. And I know there's a lot of text over there. That's just only for the astronomers who care about the properties of this galaxy. But the only things you need to take away is that this is a kind of a normal galaxy in a lot of sense in terms of their infrared luminosity, in terms of their merger stage. It's actually relatively early, and so maybe you don't expect a lot of things to be happening with it. Most of the luminosity is coming from the northern component, and so what we have is now new JWST data. It's focusing on the center here, the central 3 kiloparsec region or so, and we also have large-scale Keck KCW data that's mosaic to a much larger field. Because we want to trace how the gas might be doing on different kind of scales. So JWST gives us a lot of lines. This is a lot of lines that are of different, that can allow us to probe different interstellar medium conditions. And so here is again, you're now hopefully familiar with the 3-panel plot showing the flux, velocity, and dispersion of the different gases. And now here is, and here, we've ranked these lines in terms of the ionization potential. So what you're seeing, if you remember from the previous plot, is that we're actually looking at just a galactic disk going vertically up and down. Then as you get higher and higher ionization to higher ionization potential species, this gas starts to turn extraplanar. It starts to no longer just be in the disk, but it's actually coming off the disk at an angle. So and this is especially if you look at the neon 5 lines, this is you're seeing like high velocity collimated outflows. And so you can see in the velocity field that this kind of red and blue structure is becoming pretty apparent. So if I were to focus on this neon 5 line, you can see that it is actually pretty extended. So usually we thought about these high ionization regions to be pretty compact, but on kiloparsec, actually a few kiloparsec scale, this is one of the rare cases where we see direct line of sight in this kind of orientation being so extended. And I would have to say, this is actually kind of the limit of our field of view. So had we more pointings, who knows if we'll actually keep going. And so the cool thing about this neon 5 line is that if you look at the channel maps here, they actually kind of also have this like fork shape. And that is actually because of this is a biconical outflows. Those are tracing the walls of the cone. And we can actually see it at these resolution. And so we calculated mass outflow rate, energetics to try to put that as a piece of this puzzle. And we look at the Keck observations, which tells us the lower ionization gas is doing. And lo and behold, it is aligned in the same direction, extending much further out than what we saw for the high ionization neon 5 gas. And so we also did some diagnostics to analyze that this is likely due to AGN photoionization, meaning that it is being photoionized by the active black holes in the center. And then the last piece of the puzzle, our friend at NAREO dug into the radio archive, and they found us some radio data. Any guesses as to where that might land? So the white contours here shows the radio, the VLA 6 gigahertz radio continuum, where you can see that it aligns perfectly with that neon 5 gas, and then also it has this funny S-shaped component. And so we interpret that as a precessing jet. So we happen to have upon this theoretical paper that was just talking about precessing jet and what that would look like. It almost looks like a perfect match. You can see that if basically what it's doing is that the radio jet might be doing this wobbly dance, and we happen to be catching it at the orientation that it is, and it is basically what is powering the outflow that we see in this galaxy. So Justin went ahead to model this jet, and so here is the radio data, and then the panel B, the underlying image, is the model, and you can see that if we were to use that model and we trace out the precessing jet, it actually aligns quite well with the large-scale O3 gas that we see. So basically, try to convince ourselves, well, that is gas that's being driven by the radio jet, right? And it's not just part of the gases sitting in the halo for no good reason. And so we try to look at this in a more detailed way, trying to compare, like, okay, we know there's gas that's rotating on the galactic disk, kind of going this way, and this is what the position velocity diagram will look like. So velocity is a function of position. However, if you have this jet that's driving the outflow, and this is basically the cyan circles would look like, and that actually overlaps really well with what we see in our data. So we're pretty, we really favor the scenario where radio jet is driving the outflows that we see in this galaxy. So based on this one case study, we are saying that, at least in this case, precession is providing the mechanism for those collimated jets that may in turn drive the large-scale outflows and also prevents cooling of hot gas and suppressing inflows. And in this case, outflows may not really remove that star-forming gas. So it's not that it's not just the removing gas that's feedback, but it could also accelerate that depletion timescale because it's heating the gas, it's shocking the gas, so it's preventing star formation happening in that sense. Of course, I'm not going to answer the last question, which is one galaxy. We do have a campaign going on now with basically the JWST data that we have and also Keck data that we've already collected that are very complementary to each other, probing the circumnuclear regions versus galactic-scale regions, the different phases of the gas, the shocks and dust. And so we're putting these two together to try to understand this whole bigger picture. So Marina started to take a look at the molecular gas front, and this is just a very quick look, 1D spectrum of what's happening with the molecular gas at the center of some of these galaxies. You can already see a variety of line profiles, and I'll just point out a few of these being like 7469. I've already shown you what the H2 looks like in that galaxy. Current 273 is what, if you remember, is what we've looked at with Keck 10 years ago. Now with JWST, we're going to be doing a comparison of what we're seeing in JWST versus in Keck. And also, I like to show this IRS 01364 telephone number because it has this really strong signature of that biconical turbulent gas coming off the center. And Justin, on the other hand, is looking at things at a larger scale. So then here's kind of a quick snapshot of what all the gallery of the O3 gas that we see in the large scale compared to all of these galaxies. And you can see that this is the 10 kiloparsec scale bar. So all of these are extending at least 10 kiloparsecs out. And we have a number of lines with our KCWI data, KCRM data. So we can do all sorts of diagnostic looking at the low ionization gas and try to understand, rebuilding new models to understand like the different shocks and star formation and AGN contribution to the energetics. So takeaway points, multi-phase inflows, outflows, feedback can really needs to be, they can all happen at the same time. Then we need high resolution IFS observation in order to understand and disentangle these processes. What I did not have time to talk about are how we use the mid-infrared colors in spectroscopy to understand the nature of the hidden AGN, but we do have work on that. But I would say the verdict is still out there. It's still a little bit confusing to me, and I think I've talked to some of you in a workshop, so still trying to understand the mid-infrared lines are telling us. So for the astronomers in the audience, we have lots of references. Feel free to ask me about these later, and I will. I just want to say thank you because this is a really fun week and a half so far. It's productive in many ways, and I'll stop there. Thank you.
Thank you very much, Vivian, for that fantastic talk. Thanks so much you're able to do it. Charlie, just speak rapidly. Question. So I loved your radio jet coming up through that kind of
Do as well.
you were saying that you were interpreting that as driving the outflow. So do you see signatures of shock excitation on your coronal eject?
Yeah, so the question is, do we see evidence of shock excitation? That's supports the evidence where I'm saying that the radio jet is what drives the outflow. So let me go back to, I don't know, this is not the highest resolution image I have. Maybe I can show you that version offline. But basically, we see not only, we see not only that this is completely aligned with the neon 5, the high excitation line that we see, but also when we mapped out the turbulence gas, we see actually there's a high turbulence kind of at this point where the radio jet turns off on both sides. So over here and over here, the enhanced turbulence that is coming from shocks. And so this is probably where we think the jet is hitting the ISM and therefore before it turns off. And yeah, that's another piece of evidence that we've had this paper.
Yes, so NGC 7469. One of the fellows, that's the Richter speak for all time's sake. Anyway, I think 20 years ago, there was a very bright supernova went off in the septum nuclear ring. Did that do anything that you can see, or is it just the noise?
So the question is, the supernova from 20 years ago in NGC 7469 leave any relic signature that we can see today? I believe we did not. I don't know what I'm looking for or what I should be looking for, but I don't think we saw anything that's particularly weird about anywhere in the star-forming ring. I mean, it is a complete ring, so it depends on exactly where the supernova was. But at least within,
You know where it was.
yeah, right. But no, we didn't see anything in particular.
If you look at Chandra data, and then they made these satellite for several offsets, can people underneath find that the obscure nuclei should actually be high energy?
Yes. Okay, so the question is, have we looked at Chandra data for obscure nuclei for some of these systems? I'm going to answer that question in multiple ways, if that's okay. So in this particular system, yes, because the referee asked us to look at it. And we do have a figure in our supplemental materials that I can show you offline. So what the Chandra data looks like is that it actually has a little bit of an X-ray form, but mostly a lot of it is aligned with the gas as well, but at much lower resolution. So we, in the context of understanding feedback, we know that there's hot gas that is aligned in basically this outflow that we see. In the context of obscure nuclei, yes. So in Mercurian 273, where previously we did not detect, we only detected X-ray in like the southwest AGN. But in the north, we actually didn't see anything at first. But because of our result with the dynamical mass measurement, later on we went back with Sylvain and his student, and we got like really deep Chandra data, and we sort of make out and attune point sources in the X-ray. But for the most part, I think our existing X-ray data is probably a little too shallow to look at the really competent thick sources. But if we have more time to look, we might be able to find more competent thick sources.
Go ahead.
Not an astronomer. So you mentioned that this galaxy is created by mergers to former galaxies, and that this jet is driving this outflow. But what is the source of jet? That is just a black hole at the center? Or?
Okay, so the question is, what is the source of this radio jet? Is it had to do anything with the merger or black hole? So I did mention that this is a merger, but actually, at least from the data that we've seen, this is more like an early stage merger. So if anything, I'm not saying it should be considered in isolation, but it is. We don't see a lot of like disturbed morphology as we do in other galaxies. So if anything, it's probably not really affected by merger. That's my guess. Now, and what is this coming from? Yes, we think it's from the black hole, but why do radio jets precess? And maybe another way to answer your question, it might precess because of instability of the disk. So if you have instability, then it might start like wobbling around. Or my preferred explanation is that there may be a binary AGN in there that could cause the jet to be wobbling, and it's something that we haven't yet proved. But thank you.
Questions from non-astronomers are very welcome. Nadia, do it.
So for the star-forming ring, and that's sort of related to the supernova question, is the iron 2 completely consistent with star formation, or is there any signature at all associated with the AGN?
Yeah, so the question is about the iron in the star-forming ring. I'm going to go back to that for a second.
They tend to be strong in supernova randoms, but they could also be interesting signatures from any AGN-driven shock.
That is true. So yeah, so whether we can say anything about the origin of the iron gas in this gas, whether it's due to AGN or star formation, I think that we haven't yet done it, but I think we should be able to, now that we have more information from the stellar clusters side of we have some analysis of the stellar clusters. We have there are different lines where I'm sure like they just probe different radiation field, and so I think we can do it. We haven't yet done it. Guess I'll leave it at that.
Also related to this time too. You mentioned the destruction of small dust grain pulsation. Related, but then trace.
Yeah. So okay. So there's the question is related to this iron 2. Do we have evidence of it being destroyed of the dust grain? Like, does it actually correlate with where we might be expecting it, because it's a shock tracer and they're coming off dust grains? So I didn't do a direct comparison, but we have, when I say that this gas and this gas, they trace basically star forming disk, there's still a difference in like what relative brightness of these clumps. So these are clumpy in almost slightly different ways. And that's also true if you were to look at the pH map that I showed. Obviously, this is at much lower resolution. We do have a high resolution of this in Thomas's 2023 paper, where we have near spec and we have the 3.3 micron pH feature. So if we do a direct comparison of that, maybe we can say a thing or two, but I don't know that off the top of my head. Yeah.
I have a very naive one. In one of your plots, you showed the targeting on JWST of nuclei, very, very disturbed among Christians. How do you know where that nucleus is? Where to go?
That is $1 million question. I was like, the question is, how do we know where the center is? That is something that we, I don't want to say we never knew, but when we did our near-infrared observations with Keck, Osiris is actually a much smaller field of view than near spec and Mary. And so we always have to have high resolution HST data, so that helps. If we have colors based on near infrared colors, so maybe like different like H band, K band, 2 microns, 1.5 micron, something like that. We have colors. So we try to target the reddest stuff, which is where we think the nuclei are, which is where the dust is. That said, maybe that allows me to show something I hadn't shown before. So I'm going to show this real quick. This is a galaxy, actually the galaxy that was on my title slide, where this is basically the HST image. You zoom in, and then you see the JWST image, and then there are actually kind of 2 nuclei in there. We didn't really know with HST because they're all dust obscured, and so now we're starting to see it in JWST, but we don't know where's the active black hole, and so it's actually still not completely clear, but we can start to resolve it into different cores. And I think the radio might be some radio jets that's correlated with that one. Then we look at the spectroscopy. We find that actually the red one, the northeast course, is what's really heavily absorbed. And so when we look at different diagnostics, including like the equivalent width of the 3.3 micron line versus some other colors, we find that it's actually the southwest course that's AGN dominated versus so it's a little bit of a mess. I would say, like, if we pointed at something outside of this region, or if we missed one of the other core, we might not have known really where the AGN are. We might still not really know where the AGN are, but we have basically put together the different pieces of the puzzle so that we can have our best guess.
Thank you very much. Any other questions?
Just a really naive one from a knowledge, but I don't know that in the models that you're showing, that you're comparing to the data, these quite detailed models of dynamics. What role does that matter play? Does it play any? Does it feature in them? Is it just a bystander, or do you have to say anything about its interactions?
Well, so I will. Oh, sorry. The question is about the dark matter component, the simulations that I showed. Is that? I will say I'm not an expert, but I do work with people who are the experts. In the fire simulations, I don't know that the dark matter component is incorporated in any meaningful way. Sorry, I'm looking for a theorist friends to help out. Well, in any case, I think that at if we're talking about like nuclear scales, it may not, matter as much as opposed to, the other. It might be dominated more by the black hole gravitational. I don't know about the larger scale, though, of course.
Thank you.
No questions from non-astronomy?
You mentioned the chicken and the egg in the beginning.
Yes.
So,
Is there an answer to that?
how to answer that question? Or
Yes, so I mentioned the chicken and the egg. Why did I put that in there? And basically the question is, do we have an answer to whether the bulge comes first or the black holes comes first? I have my preferences. I'm not sure. Let me see if I have a slide of that actually. So maybe I took it out. Okay, sorry. So when we look at our galaxy mergers and we try to make them on that M sigma plot and try to understand, did the black holes, are they the ones that's driving the galaxy bulge to grow or vice versa? We found that our galaxies tend to lie on top of the relation. So, which means that on an axis where you have black hole mass growing and you have the galaxy growing, we're saying that if you have a galaxy that is gas rich and is going through this merger process, chances are a lot of gas is getting funneled into the center very quickly to be growing the black holes. And then we think that maybe because of the positive feedback that we saw and other people saw, maybe that's what allows the galaxy bulge to catch up. I will say that particular conclusion has a few caveats. One is that it probably is very selection effect dependent. If you look at like some dry mergers, for instance, I think there are people who found that dry mergers tend to lie below the scaling relations. And also, we're always limited by, these are enclosed masses, which we think are pretty close to or within the sphere of influence. But we are also trying to improve those black hole mass measurements by looking at like the amount of gas that's actually sitting in kind of enclosed space to see, okay, is that gas that we measure really on the black hole, or is it like just sitting around waiting to be accreted onto the black hole, in which case that would completely alter the time scale that we might expect for them to fall onto the black hole. So we have thought a lot about it. I'm not sure we have an answer that I'm willing to die on at this point.
One last question? If not, let's start with Vivian again. Thank you.